I'm Dr. Jennifer Ripley, and I'm going to be covering some underlying principles behind the t-test in statistics. So we're going to be looking at some major concepts, and I'm going to review those for you right now. They are, number one, what is within group variance and between group variance? How does that work in t-tests? Number two, how do bell curves relate to t-tests? Number three, why is variance important? Why can't we just look at the mean score differences? Number four, what's the formula for t-tests mathematically? And number five, how do degrees of freedom and sample size fit into all of this?
All right, for t-tests, we're going to look first at the big picture. So first of all, remember that when we're doing a t-test, we are looking at grouped or categorical independent variable and a continuous dependent variable. So if you look in your textbook or you look at other textbooks that have statistics maps in them, they kind of show you what kind of variables you have and then what type of statistic goes with it. When it comes to t-tests, you're going to have a categorical independent variable that only has two groups. A t-test can only handle two groups maximum. An ANOVA could handle 3 or 4 groups or more. And an ANOVA can also do two groups, but the t-test can only do two groups, comparing two groups to each other on the continuous dependent variable that goes with them. So we are primarily looking at differences between groups and trying to determine if those differences are with the probability of p.05 caused by the independent variable, right? If there's not a difference between the groups, then your probability is going to be larger than 0.05. And if it falls below 0.05, then we decide that the two group difference is actually statistically significant. So an example we can use in this is the difference between the classic drug Prozac and a new drug in the treatment of depression. So say you have mean scores, and the higher mean score means that you have more happiness or more enjoyment in life. So your hypothesis in this case would be, does the new drug that you're testing, is it better able to predict happiness than Prozac? Is the higher number on the new drug, or is it the same as Prozac, right? Are those two groups different from each other? The t-test is the statistic that can answer this burning question, and it's a really interesting question, I think. Okay, so the t-test is a statistic that can answer that burning question, and it is an interesting question. So if a researcher asks this question, what she's saying is she has two independent samples. Notice that the word independent is highlighted, meaning that the behavior in one sample is not related to the behavior in the other sample. She randomly assigned a group of people to the two groups. That's the most common way of having two groups. Sometimes it's not always possible to have two groups that way, but that's the most common. And that means that they're independent. If you're in one group, you can't be in the other group. You're only in one group. You're either getting Prozac or the new drug. You're not getting both. Okay, that's an absolute necessity for a t-test to work properly. She can then run an independent samples t-test to compare the means and their variances and see if they're significantly different than each other. So relate this back to our hypothesis. What would the hypothesis be for this one? She is asking, is there a significant difference between new drug and Prozac in happiness scores? And the null hypothesis would be there is no difference between the groups. And so what would be called the research or alternative hypothesis would be that there is a significant difference. Okay, what the researcher is actually doing is she is comparing the groups, the two groups of her categorical IV on her continuous dependent variable, right? And she's actually comparing the distribution of them with the other group to find out at what point do the two bell curves show themselves to be different from each other. They separate enough to be different. And that point of separation is critical. There's a critical value where the differences are improbable as a function of chance. So you can see here in this picture, you've got two bell curves. One is Prozac and one is the new drug. So let's say everyone who took the new drug, they're on the red bell curve, right? So if you just look at the red bell curves, you can see how happy people are on that is varied. Some people are kind of high, some people are kind of low within the red bell curve, and some are kind of in the middle, right? Most people are in the middle, bunched up. So everyone taking Prozac is also the same thing in the blue bell curve. You'll have a bell curve of each of your groups in your sample. So if you take those two bell curves, you can actually see here several different possibilities of the outcomes of the bell curves. You see the first one in the top left, that one has the red and blue bell curves are practically on top of each other. It's really clear there's no difference between them. They almost have the same mean score and about the same variance too. There's no difference. But then you go to the next one and they spread out a little further, and then you can spread them out even a little further. And there's a point at which if the data looks like there's no chance that the difference between them is just due to random factors. Instead, you think the difference between these two bell curves is actually caused by the drug. And we can assume in our research, if it's done well, that the cause is the medication differences. It's not just the mean scores, though, and that's what I want you to pay close attention to here. It's the variance, right? It's very important that those bell curves are varied for each other. Okay, so what's really important here is to remember that it's not just the mean score difference that tells you whether two bell curves or two groups are different from each other. It's actually also the shape of those bell curves, whether they are mesocurtic, platycurtic, or leptocurtic. So if you remember in previous lectures from me, you got a little information. You've got here a picture of some platycurtic curves on top. They're the really flat ones, really long and flat. And the leptocurtic on the bottom, those are really tall and skinny, right? And you'll see on the bottom ones, they have low variability within each group, meaning everybody in group 1 and group 2 are in a small space, right? Whereas in the platycurtic, you have high variability, a large amount of variability, meaning everybody in group 1 is all spread out across the number line, right, at the bottom. And the other group, same way, they're all spread out. So what you get is when you have two leptocurtic curves, they don't have to be very far apart, and the curves are completely different from each other. As you look at them here, you can see that the two curves on leptocurtic, they don't overlap with each other at all. There's not a single person in the wrong group, right? Whenever you put them together, but the platycurtic is, and if you look closely here, assuming this was on the same number line, their mean scores would be exactly the same. So the mean score is right at the peak, the top of the curve. So you can see the peak of each of these curves is really about the same, but you can't tell which group the platycurtic people were supposed to be in. There's so much overlap, but you can really easily tell when you have a very small within group variance. You get a lot of separation with them. Okay, if you have medium variability, it's kind of in the middle, and then there is a certain point at which the groups are far enough apart. But what's important is it's not just the means that are getting pulled apart, it's the entire curve. So you need to know both the mean and the variance. It's because it's based on that score. At some point, there's such high variability that it's very important. You'll never know what group is different if you have high between group variability. What that means is that the mean scores are far apart, right? And then if you have low within group variability, right, like the bottom picture there where everyone's clumped together, that's a nice leptocurtic curve, then you are going to get significant difference. If you have platycurtic curves, like you see in the picture in front of you, you're never gonna be able to tell which group people are supposed to be in, and you have high within group variability, and then the same amount as the other one of between group variability. And then your probability is never going to get below 0.05. And that means it's hard to publish things when things aren't significant. And it just kind of makes you sad. So this is a very important point about exactly what's happening behind the scenes when you're doing a t-test. The same concept will be applied to ANOVA. So it's important to understand we're looking at differences between two groups for a t-test and two or more groups in ANOVA. And we have to judge the difference between their mean scores. So that's their between group variability is the mean score difference. And their within group variability, which is each group's variance. Make sure you understand this concept that we're looking at. It's not just the mean differences. Okay, so when we're comparing two groups, we've looked at the mean, we've looked at the variance. You've got that now. But remember, there's another aspect to each group. Each group has its own sample size. And those sample sizes are not always equal because even if you randomly assign people equally to two groups, things happen in the real world. Maybe there was a lab mix-up. Maybe the lab rat died. Maybe there's things that exist in the real world. If you're comparing people and you want to look at gender, you're going to find a lot less men in a Psych 101 class if you're sampling a Psych 101 class, and you're going to find a lot less people who are not gender conforming. So you're going to have unequal n if you're trying to look at that variable, as well as even if you randomly assign people to groups, things happen. People decide to quit the study, and you get all kinds of different dropout rates, especially if you have a large sample of people. So you have to know that you may not have the exact amount of people in each group, even though in an ideal world you would. Now, here's an important statistics lingo point for you, okay? A denotation that I want you to remember whenever you're reading articles or you're putting together a poster for a presentation and you're working in the profession, the capital N is the denotation for the total number of participants in all the groups in the entire study. And a lowercase n is the number of participants in a single group that you're comparing. So in this case, the people who took the new drug group, how many people were in that? And the people who were taking Prozac, how many people were that? If you add those up, the new drug plus the Prozac, that's your capital N. But your lowercase n is how many people are different. So maybe you have different numbers. Say you had a couple people drop out of your new drug group. So you ended up with like 48 people in that group. When your Prozac group, nobody dropped out and you had 50 in that one. So your lowercase n would be 48 for the new drug and 50 for the Prozac, which means your capital N would be 98. Right? 48 plus 50. So when you're reading articles or you're presenting your own data, make sure that you use the capital and the lowercase correctly. Okay, this is the t-test formula. Please do not be afraid of it. It's really not that bad. And I'm going to walk you through it. And we will first of all go here and see that the X with the line over it, right over it, the X with a line over it is a mean score. So that would be the mean score of group 1 minus the mean score of group 2 that you're working with. So in our example, we might assign the new drug to be group 1 and the Prozac drug to be group 2. And we're just looking at what's the difference between them. You would probably use that right here to indicate the difference of one minus the mean of the other. So really all that is the difference in the means right on the top there. Very simple. That represents between group variance. Okay, so we're looking at the between group variance on the numerator in the formula because it's looking at the people there. Okay. Then you go down to the denominator. What you have there in an S is the measure of variance for each group. So the S stands for the variance, okay, in this formula. So S would be the variance in group 1, and you're going to square it. And then it's over lowercase n. So we just learned lowercase n is the number of people in that group. So the number of people in group 1. So it's going to be the variance in group 1 squared over the number of people in group 1. And then you add to that the variance of group 2 over the number of people in group 2. Okay? And then you square root the whole thing. The squaring and the square root, that standardizes everything. But what you have here in the denominator is a representation of the within group variance, right? So each group's variance with the number of participants is calculated there to give us the t-value. The larger the t-value, the more likely you have a difference between the groups. Because remember, if the numerator is larger, there's going to be a bigger difference between the top numbers, right? Large numbers. And it's in ratio to the bottom number, which is a measure of within group variance. So big between group variance and small within group variance is going to give you a big t-score. And then you'll check the probability to see if that is significantly different. What I want you to know is the principle behind that. This takes us to the issue of degrees of freedom. This is a really important concept that I know a lot of students struggle with when they're first starting out in statistics. So I want to walk through the concept of degrees of freedom and how it relates to the number of values and the sets of scores and how things are free to vary after certain restrictions are placed on data. So we have an assumption in all of statistics that the mean score in a set of data can be known, that it is a particular number. So if you sum up all of the scores and you divide by the number of participants in the study, you will get a mean score. So we know that that's true in how numbers work. So we can play around with the numbers a little bit, and we say that 4 people, you see these 4 lovely people here, 4 people, we know their shoe size, okay? And because we know what their shoe size is, if the mean score can be known, then that means that 4 people's shoe size in a group of 5 are free to vary, meaning they can be pretty much any score that they end up being. Like if you're being very concrete, it's like, well, what is their shoe size actually? Well, it means that in the conceptual thing, they can be any number. It doesn't matter what number they are. However, once you get to that last person, that last guy there with the glasses and the suit on, his shoe size would have to be a certain number in order for a particular mean score to be true. So it's kind of a backwards way of thinking about data. But because this principle is true, because the score on everybody in the group is always going to be calculated, and because we can assume that no matter how many scores, we can always figure out that final one. So because that's true, we can do what's called the degrees of freedom. So if we have 4 people, they can give me a score. It doesn't matter what those 4 numbers are, but once the 4 numbers are locked in, the 5th number has to be a certain number, because when you add up the 4 numbers, they could be any number, but when you do that final number, it must be the missing number. So this becomes like a formula, just like algebra in middle school. You might be asking, why do professors always teach this concept? That's because the degrees of freedom concept being true is a really fundamental concept as to why statistics works at all. The degrees of freedom tells you how many participants you have in your study, too. So this is like the practical, useful thing for graduate students who are reading articles. As you go forward, you can always figure out the number of participants in a study by knowing, well, the degrees of freedom. So in this case, if I'm told the degrees of freedom in a single group, right, maybe this is our Prozac group here in front of us, but a single group is degrees of freedom is 4, then I know, that's going to be a 5-person group. And the same thing with the other group. We can have whole other group of people, right? And they're taking the new drug. And so we would know how many people are in there. So what you should be able to do is calculate it both directions. You should be able to take mean shoe size or mean happiness score or whatever it might be of your dependent variable in a frequency distribution on 5 or 6 people and be able to figure out what that final person's shoe size would be if you're given the mean score. And so you can calculate the degrees of freedom. You should also know that the degrees of freedom is n minus 1 for each group, right? So n minus 1 for the Prozac group and n minus 1 for the new drug group, right? So in this case, that's 5 minus 1, which is 4. So I hope this has been helpful to try to think through the degrees of freedom and understand, but most articles in psychology don't actually report the lowercase n's all the time. So sometimes you have to pull it out of the degrees of freedom. So as we go forward in learning in this class, make sure you pay attention to the degrees of freedom because they give you the clue on what the sample size is. And finally, I just want to do something fun for the end, a little bit of the history of the t-test. Gossett was one of the people who created the Guinness beer. So if you like Guinness beer, this would be your guy. I believe it's William Gossett. And he discovered the formula for the t-test curve and got p-values to be able to compare means because he was doing small samples of beer and he was comparing one beer way of brewing, right? And the hops that were in it. He was comparing one to another and the barley in this other one to produce more consistent beer. So he would try different types of barley and compare them and then run t-tests on them to see which one was better. So he was just a really interesting guy. This was like super early in the world of statistics and one of the first statistics that was ever done. And he kind of cute. I think he's kind of cute. So this is early beer science and statistics science overlap with each other along the way. So enjoy this little bit of history.